given. So what is optimization? Okay, a structural engineer may seek the dimensions of a beam that maximize strength for a specified cost. A packaging designer may seek the dimensions of a container that maximize the volume of the container for a given surface area. Airline strategists need to find the best allocation for airlines among several hubs to minimize fuel costs and maximize passenger miles. Okay, so we're trying to be efficient pretty much. Okay, now the point, I know that was like a lot of like big words, big things going on. We're going to find an applied maximum and minimum value. So we're finding the absolute max and min like we've been doing, except now there's a scenario behind it. That's it. Okay, so we're going to find the max and min just like we've been doing, except now there's a scenario behind it, and we have to take all of those things into account. Okay, so our guidelines is we're going to read our problem, draw a picture of what our problem is saying, and then write, draw a picture and assign variables, and then write max or min and the quantity to be optimized. So we're going to read our problem and say, okay, are we trying to find the maximum area, the minimum volume? What are we trying to do? Okay, whatever we decide, we're going to write an equation for the expression in step 2. So if we're trying to maximize the area, which is something that we do a lot with these problems, well, the area of a rectangle is length times width. So that would be our equation for our expression. Okay, then steps 4 and 5 are where it gets interesting. Okay, it says write this equation as a function of one variable using other facts. Okay, what we're going to try to get to is we're going to try to get to taking the derivative. Okay, but we only want to take the derivative with one variable, not two. So if we have length and width, we only want to have L's, or we only want to have W's. Well, the way that we're going to do that is use all of the other stuff that's in our problem. Okay, the other stuff in our problem, and there's always going to be other stuff, is going to lead us to where we could solve for another variable and plug that into our equation. Okay, once we do that, step 5 says optimize the function over its domain. That's very mathy. That means we are going to take the derivative, set the derivative equal to 0, and solve. That's what we've been doing this whole time, right? Taking the derivative, setting it equal to 0, and solve it. Okay, and then we're going to answer what is asked, right? Most of the time, that's whatever we found. Okay, we might have to do a little bit of tweaking, but not much. Okay, so we're just going to work, I think, 5 examples of this stuff, and then after we get done, I'm going to give you some more time to do that homework that is due. Okay, because I know it's tough, right? Those 2 problems of the graphing. So I'm gonna give you all some more time for that. Sound good? Okay. This says a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the fence that will produce the largest area? What is the maximum area? Okay, so draw your picture, assign your variables. That's your first step. So there's my river. There's what my fence would look like if I put a fence around the river that borders it, right? And then we can assign variables. We can say X and Y. You could also do L and W, length and width. Doesn't really matter what your variables are. Okay, then we want to know what we're looking for. Obviously, we're looking for the max area, right? That should be easy to figure out, right? So we're going to look for the max area. Okay, well, the area of that would be Length times width, right? X times Y. That would give us the area. Now, we need to use our other facts so that we can solve for one variable, right? We only want X's or we only want Y's. So we have to use all of our other stuff. Well, specifically for this picture, you have X along the bottom and you have Y, right, as your length. Well, this is also Y, right? We also know that we only have 2,400 feet to work with, right? So our picture would be Y plus X plus Y has to equal 2,400 for sure, okay? We can simplify that and say 2Y plus X is gonna equal 2,400, okay? The easiest variable for you to solve for would be X, right? You can solve for Y if you want, but I would suggest working smarter and not harder, right? This is already pretty difficult. So if we move 2Y to the other side, we would have that X equals 2,400 minus 2Y. Well, we can take that and plug it in for X in our problem, right? So you have A equals X, which is 2,400 minus 2Y times Y. I'm gonna write that again. Okay. Well, I can clean that up a little bit. I can distribute and say I can distribute that Y. And so I get 2,400 Y minus 2Y squared. Okay, that was your third step. That was write an equation for the expression in step 2 and write this equation as a function of one variable using the other facts. That's what we did, okay? Now we need to optimize it. So that means we're going to take the derivative. Okay, so that would be, let me change my colors. 2,400 minus 4y. Okay, then we're going to set our derivative equal to 0. And solve. So you would add 4y to both sides, divide by 4, and y equals 600. Okay? So the length of y is 600. Our question says, what are the dimensions of the fence that will produce the largest area? And then what is the maximum area? So we need to know what x is as well, right? Okay. So we know that x is 2,400 minus 2y, and we know what y is. So we can just back substitute now, right? So we're going to take this, plug it in there. So x is 2,400 minus 2 times 600. And that would give us 1,200. Okay. So we need to write our answer. So our dimensions would be 1,200 feet by 600 feet. That's our first answer. And our next question was, what is the maximum area? And max area, you would just multiply those together. 1,200 times 600 gives you a big old number. And we're going to have feet squared. Okay. Everybody good? That's not so bad, right? It's not. Okay. Let's try this one. All right, so what these are going to do, they're just going to get a little bit more complicated each time. There's going to be one little more trick, right, in it. So it says the Cannon family has decided to earn, that's what say earn, not early, earn a little extra money by raising puppies. Since they will be raising 3 different breeds, they need 3 separate kennels. The Cannons decide to build a rectangular kennel with 50 feet of fencing and divide that kennel into 3 equal parts as shown below. Find the dimensions that would maximize the enclosed area, okay? So I drew the picture for you, right? And then if we're labeling stuff, we could label X and Y, right? And we're looking for the max area, so that's pretty obvious once again. So that's X times Y. So we have drawn our picture, given it some variables, said what we were trying to find, and we've written an equation for that, right? Okay. Now we need to write our equation with one variable using our facts, okay? So what we have going on here is if the bottom is X, then the top is X, right? And then if the side is Y, this side is Y, but also this length and that length are Y, right? So we have 2 X's plus 4 Y's give us, how many feet? 50? Yeah, 50 feet of fencing, right? So again, you could solve for X or Y. I usually just solve for X. I don't know why, but I do. So I would move 4Y over. And then divide each term by 2. Negative 2Y plus 25. So, kind of like we just did on the other problem, I'm going to plug in negative 2Y plus 25 for X. Okay. I'm going to clean it up. And get negative 2Y squared plus 25Y. Then I want to optimize it. So that means I'm going to do what? Take the derivative. Negative 4Y plus 25. Then I set that equal to 0. And I solve. So I add 4Y to both sides. Divide by 4. We can leave that in decimal. So 6.25 is what we got for our Y value. Okay. Our question says, find the dimensions that would maximize the enclosed area. So we have one of the dimensions, we have Y, but we don't have X, but we know that X is negative 2Y plus 25. So we can just back substitute and plug in 6.25 for Y. Will be negative 12.5 plus 25, which is 12.5. All right, so your dimensions, your X needs to be 12.5 feet, and your Y 6.25. Terrible box. Also a terrible box. Here we go. Okay. Everybody good? All right, next one. I kind of already have this pre-drawn because I'm a horrific drawer and I didn't want to do that in front of you and you make fun of me. So I did it before I got in here. All right. Not that you guys would ever make fun of me, but so I'm going to give you just a second to write all that out. Okay. It says a square piece of cardboard with 12 centimeter sides is to be formed into a rectangular box by cutting squares of length X from each corner and bending up the sides. What value of X would maximize the volume of the box? Okay. So we really amped it up with this one, right? So we know that we're trying to find the max volume, right? And volume is length times width times height. All right. And so we have this square piece of cardboard. We know that the sides are 12, and we also know that we're cutting out squares of length X from each corner and bending up the sides. All right. If you are not a very visual person, which I am not, this is hard for you to see, right? Even though I do have this picture right here, which is if we folded the box up, if we folded the sides, it's kind of hard to see. So I got a piece of paper and I cut out little squares on the sides, right? And then I folded the sides up. I felt kind of silly in doing this in my office, but I did it just for you guys. Let me see. Fold back. So I folded them up and it makes a little box, right? Okay. So this is what we're actually dealing with. That's what it looks like 3D when we write it out, okay? It wants to know what value of X will maximize the volume of the box. So whatever length we cut out for X is how much we're folding up, okay? So look, it's this part. It's the sides. Okay, that is our X, right? If I cut out to here, then I'd have to fold to there, right? And so I'd be folding up more, okay? So whatever that length is, that box count. These will trick you out too if you look at them for too long, right? All right, so we can label our box like this. Also, why this is a little more complicated is we have L, W, and H, right? But let's look at the length, the width, and the height of what we actually got going on here, right? This whole thing is 12. But I'm cutting those X's out, right? So I'm gonna do it on this side too. That's 12. But this just that piece. So I'm taking off those X's, right? You see? Would be 12 minus 2 X's, right? I'm cutting them off. Same thing on the side, right? This piece would be 12 minus 2X. So what we really have going on here is this, which would be the length, and this which is the width, is actually 12 minus 2x, right? This piece is 12 minus 2x, and so is this piece. So it's 12. I'm going to use my colors. And this side is 12 minus 2x. Okay. Well, that means that if we have length, width, and height, our length is 12 minus 2x. Our width is what? 12 minus 2x. What's our height? X. Yeah, x. So if we substituted all that in, we would just be dealing with which variable? X, which is great. Perfect. Okay. So let's substitute all that in. My length, no color, purple. 12 minus 2x. My width, 12 minus 2x. My height was x. Okay. Sorry. Someone's asking me if I want anything from Chick-fil-A, so I'm answering. The answer is yes. Right? Sorry. All right, so now let's clean this up. That can be cleaned up a lot, right? I'm going to distribute that x to the blue to clean it up. So I'm going to say, I'm not going to touch this 12 minus 2x. But I'm going to make this 12x minus 2x squared. Like that. Okay. Now I'm going to FOIL that. So that's 144x minus 24x squared minus 24x squared plus 4x cubed. Okay, so I'm going to put it in descending order and add my like terms on the next line. So 4x cubed minus 48x squared plus 144x. Okay. So I'm going to take the derivative of that. That would be 12x squared minus 8x. Oh, 48. Were y'all going to correct me on that or just let me mess it up? Huh? I can always tell because some of y'all's facial expressions is not like the normal way that you look at me, but you're like, should I tell her or not? Sorry. So 96, my bad. X plus 144. Okay. I'm going to set that equal to 0. And I'm going to factor it. Well, I can take out a 12. There's the 8x. All right, so I can factor that. Okay, so I would get that x equals 6 and x equals 2. Okay, so if you get to a point where you get 2 answers, one of them is going to make sense, the other one is not. Okay, so we have 6 and we have 2. I want you to look at what would happen if x were 6. Yeah. Does that make sense? No, that does not make sense, okay? This doesn't make sense. Right? This one does. This is the only answer That makes sense. So x equals 2. I only asked for the value of x that will maximize the volume. So x equals 2, that's your number. You would want to say 2 inches, right? If I asked you for the length and the width, you would just plug in 2 and get that it's 8. So I didn't ask you for that, but if I did, that's what you would do. Sorry. Centimeters. Okay, any questions on that one? That one's hard because it's hard to think about and visualize, right? I'm, like I said, I'm not a very visual learner. Physics was not my friend. Very sorry. I know it is some of your friends in here. But I was like, I don't see it. I can't see it, right? But this helps a lot whenever you can actually fold the paper and stuff. All right, 2 more and we'll be done. This one says a rectangular page of a book is to contain 90 square inches of print. The margins at the top and bottom of the page are each 1.5 inches, and the margins on each side of the page are 1 inch. What should the dimensions of the page be so that the least amount of paper is used? Okay, the least amount of paper is used. Okay, so you have a rectangular page of a book, and then you have 90 square inches of print. So that's what the black page is. That's why I have it scribbled. That's where the print's going to go, okay, on the page. It says that we need to find the dimensions of the page so that we're using the least amount of paper. So you want to find the minimum area. So we want to minimize the area of the outside rectangle. So the blue. We want to minimize the area of the outside rectangle because we want to use the least amount of paper. Okay. Well, now we're back to areas length times width, right? And we have some stuff going on. Okay, so let's look at our picture for a second. Okay, we know that the black rectangle has an area of 90, right? So you would multiply your length times your width and get 90 for sure. Okay, we also have some stuff going on in the margins, right? So it said the top and the bottom are 1.5 inches. That's the margin. So that means that this right here is 1.5, and so is at the bottom. And then on the sides, it was 1 inch, right? Yeah. This was 1 inch. Okay. So we are looking for the area for the outside rectangle. So we need this length. Oh man. We need that length, right? And we need, use another color, this width. whatever. There we go. It's infuriating. Okay, so let's see what's going on. We have, I want to stand up, but I also am doing this on Zoom. So if I'm finding the orange, I have this part is 1.5. Okay. And then we have L. We know that we know something about this length because we know the area, right? So we're going to say plus L, which would be the black to the black. And then we have another 1.5, right? So plus L plus another 1.5. All right. So our L over here in the light blue for our outside rectangle is actually 3 plus L, right? 1.5 plus 1.5 is 3 plus L. So we're going to write 3 plus L for the outside rectangle. We're using what we know about the inside rectangle and the margins to figure this out, okay? So we're going to do the same thing with the width, okay? We know that that's 1 plus W plus 1. So that's 2 plus W. So times 2 plus W. Now, we still have an L and a W, right? But we know something about the inside. We said that the inside rectangle, that area is 90. Length times width gave us 90, right? So we can solve for 1. We can solve for L. And L is 90 over W, right? So we can go into our equation up there with the blue, orange, and pink and put 90 over W in for L, right? So we can say A equals 3 plus L, which we said was 90 over W, times 2 plus W. Okay. Everybody okay so far with what we've done? Okay. So let's FOIL this guy. So that would give us 3 times 2, bless you, is 6 plus 3W plus 180 over W plus, bless you, 90, right? So we would do 90 over W times W. So W over W, you mark it out, you get 90. Everybody okay with that? Okay. So we can clean up a little bit and get 96 plus 3W plus 180 over W. All right. Now we're going to optimize it. So we're going to take the derivative, set the derivative equal to 0. All right. So we're going to take the derivative. So derivative of 96 is 0. So we have 3. We need to take the derivative of 180 over W so we can move that W up and make its exponent negative. Right? Okay. So if we took the derivative of that, we would get negative 180 W to the negative second. Right? So we're going to write that in. Okay. I'm about to set this equal to 0 and solve. So I don't want a negative exponent there. So I'm going to move W to the negative second back down before I set it equal to 0. Now, I'm gonna set my derivative equal to 0. And I'm going to solve, so I'm gonna subtract 3. Then I'm gonna multiply both sides by w squared. And divide by -3. So I get w squared equals 60. And I'm going to take the square root of that and get 7.75. Okay. My question asked me, what should the dimensions be of the page so that the least amount of paper is used? So I found that 7.75 is my width, and I know that my length is 90 over whatever my width was, right? So I can grab this, take it over here, and say, okay, well, L is 90 over 7.75, which gives me 11.61. So my dimensions should be 7.75 inches by 11.61 inches. That should be the dimensions of your paper. Any questions on that one? Oh, I didn't know who was talking. Yep, go ahead. You're hidden. I took into account my 1.5 and 1.5. Yeah. I would have had to do that if I just used L and W, but I did 3 plus L, 2 plus W. Good question. All right, last one. This one says a rectangular storage container with a top is to have a volume of 10 cubic meters. The length of the base is twice the width. Find the dimensions of the box produced that would minimize the amount of material. Okay, that would minimize the amount of material. So anytime that you hear amount of material, that means that you're going to look for the surface area. So we want to find the minimum surface area. Okay. Now, the way that you find surface area is you want to find the area of each side of your container, right? I want to find the area of each side. Okay, so I'm going to do some coloring on my box. Everybody good? Drawing the cube. Y'all know how to do that? It's tough, huh? So I'm going to try to do it, but if you make fun of me, you're a loser, okay? So draw a square like that. And then draw another one kind of like over here. And then connect like that. Like that. Everybody okay? Yeah. Yeah. If you're a visual person, it's way easier. I'm not, so I'd use the little trick. Everybody good? Good. Not everybody at once. Thank you. All right, so now, if we're gonna find the area of each, let's put some labels here. So this is gonna be the length, the width, and then here's the height of my box, right? So I have the bottom of the box is here. That's the bottom of my box, which has the same area as the top of my box, right? Right here. Right? Well, that's just the area of a rectangle. So that's length times width, right? So that's, and it's literally L times W. And I have two of them, right? I have a bottom of my box and the top of my box. So I have 2 times length times width. Okay, let's do the sides of my box. So I have this side would be the same as that side, right? And what are the dimensions of that? Width times height. And there's also 2 of those, right? I have 2 sides in my box. So that would be plus 2 times W times H. Then I have the front and the back. So that's this part and the back. And that is what times what? Length times height, and there's 2 of those. So 2 times length times height. Okay, so a lot of shading going on. If you don't have any colored pencils, it's tough. Okay, now there's a lot going on in that equation over there, and we need it to be in one variable. And right now there's L, W, and H. Okay, so let's use whatever else we know. It says that the volume of the container is to have, the volume is 10 cubic meters, right? So the volume of our container, which is length times width times height, has to be 10, right? Our volume is 10, okay? We also know that the length is twice the width, right? Twice the width. It said that in our problem. The length of the base is twice the width, okay? So we could substitute 2W in for L for sure, right? So then as long as we could write H in terms of W, we'd be good. We would just have W's, okay? So we're gonna plug that in all at once, so just hang on to that. So if I know that L is 2W, then I could plug it in here. And I could clean up. I could divide by 2W squared and get 5, right? 10 over 2 is 5, and W squared still in the bottom. And that would give me H in terms of W. 5 over W squared. Okay, so I used what I know from my problem to figure out that I can turn everything in terms of W. So I'm going to go and plug in all of that information. So my surface area is going to be 2 times L, which is 2W, times W, plus 2 times W times H, which is 5 over W squared, plus 2 times L, which is 2W, and H, which is 5 over W squared. So a bunch of W's. Okay. So let's clean up each of those real fast. So that's 4W squared. Plus 2 times 5 is 10. And then W over W squared is just 1 W in the bottom, right? So 10 over W. Plus, you have 2 times 2 is 4, times 5 is 20. And then same thing, W over W squared would leave you with W in the bottom. 20 over W. All right. Well, 10 over W plus 20 over W, those have a common denominator. Okay. So I'm just going to make a little note. So these. In the next step, I'm going to notice that they have a common denominator. So I'm going to add the numerators and get 30 over W. But I'm going to move W up, because I'm about to take the derivative of it. So I have 4W squared plus 30 W to the negative 30. So plus 30 W to the negative 30. Now I'm going to take the derivative. So I would take that negative 1 to the front. So I'd have minus 30 times minus 30 W to the negative second. So I would move that W to the negative second to the bottom. Okay, so I'm going to do that all in one step. Minus 30 over W squared. It's the same thing I did for the last problem. Set it equal to 0. And solve. So subtract AW multiply by W squared. And then I would divide by negative 8. That gives me 3.75. I'm going to take the cubed root of both sides and get 1.5. Okay, well, that is my width, but I need my length and my height. So I have these guys over here that I can plug into, right? So length is 2 times W, so that'll be 2 times, what was it? 1.55. And that would give me 3.1. Do the same thing with my H. Plug in 1.55. I'm going to square it. That gives me 2.08. So if you want to write them all together, your width should be 1.55 meters, your length 3.1 meters, and your height 2.08.